Hello there, everybody. Welcome to an exciting episode of HL Chemistry Flip Classroom. Today we're going to be talking about the basics of atomic structure. Before we do that, though, let's look at a picture of a raccoon rolling down a hallway. Because why not, right? But, as I said, we're going to be talking about atomic structure today. That's the main thing we're going to be talking about. And a fair question to ask is, how do we know that atoms exist? Do, in fact, we even, air quotes, know atoms exist? And that's something you can debate in your theory of knowledge class. But I think it's worthwhile to look a little bit about how we developed some of the ideas that we did about the atom. And so, one of the first guys we're going to talk about, his name was John Dalton. And he's kind of the father of the atom, if you will, or given credit for developing the first atomic theory. And the way he did this was just by really carefully taking some measurements, performing some chemical reactions, and carefully measuring the results. So he developed a model of the atom, and we may or may not have talked about models of the atom, but a model is just an idea. And our model of the atom has changed over time, but his model of the atom really was basically just a sphere. And he said that all elements are made of these spheres, these atoms, and these atoms would have had different masses. So an oxygen atom is heavier than a hydrogen atom, for example. And all of matter is made by just some sort of rearrangement of these atoms. And while he was a little bit incorrect from what we believe now about his model of the atom, really most of what he says directly applies today. And I would say almost all of the chemistry we look at, we really can just be thinking about a Dalton model of the atom when we do it. So his model's not perfect, but it still works, which is something that can be true of scientific models. Then there was another guy. His name was J.J. Thomson. He used a little device called the cathode ray tube. And I'm going to let my buddy here talk to you about what exactly a cathode ray tube and what J.J. Thomson did.
To demonstrate a Crookes tube, a cathode ray tube, we need a high voltage power source, such as this one. We need the Crookes tube, which has a metal cathode, a metal anode, a screen that has been coated with a phosphorescent material that gives off light when struck by electrons, and a bar magnet. As we turn on the screen, we notice that electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated. We can use a magnet to show the deflection of that stream.
Here we can see the electrons being deflected by the magnet. The cathode ray moves upward. If we reverse the magnet, we would predict that the beam would be deflected in the opposite direction.
Okay, I think you get the idea there. And by the way, do you guys realize that you're watching a YouTube video of somebody else watching a YouTube video? It's pretty crazy, huh? Anyway, so J.J. Thomson knew that there are these particles. He knew there was some sort of particle that could be made to move across that cathode ray tube, and he knew they had a charge. He assigned it a negative charge. So he discovered that there is some sort of particle with a charge inside the atom. I think he called them corpuscles originally, but we call them electrons now, and given a negative charge. So basically, he has what's called a plum pudding model. A plum pudding model, I've never had plum pudding. I think it's a little bit like bread pudding. Have you ever had that? If he had been alive today, he might have called it a chocolate chip cookie model. But imagine a chocolate chip cookie where the actual cookie is sort of positiveness, and the chocolate chips are electrons kind of embedded within it. And so that was his notion of what an atom was. So notice that we're improving upon Dalton's model. We're adding things to it. We're adding electrons to it. Still not quite how we think an atom to look like today. Another big-time experiment that came along was this guy named Ernest Rutherford, who is a scientist and yeah, so you don't need to worry about that slide that I skipped there. That's just a duplicate. But he conducted something called the gold foil experiment. And the piece of the puzzle that he added is that atoms have a very, very small, relative to the size of the atom, nucleus where the positive charge is, and all the rest of the atom is empty space. And in fact, atoms are more than 99.99% empty space. So that means you, since you are made of atoms, and the pencil you might be holding, I hope you're holding a pencil and taking some notes, the pen or pencil you might be holding, the chair you're sitting in, all of these things are made of atoms, and all of these things are more than 99.99% empty space, which is a pretty crazy claim if you think about it. How could he possibly make such a claim? Well, let's see. We're going to look a little animation of his gold foil experiment.
In the early 1900s, J.J. Thomson proposed that
I could just take a look at this.
based on Thomson's model, Rutherford expected that the positively charged alpha particles should pass through the uniform sphere of positively charged matter with little or no deflection. Click on actual experimental results to see what actually happens.
So basically what we're looking here is radiation being emitted from this little box. These are alpha particles. They're very small. You can't see them. They're actually helium nuclei is what they are. But he's shooting them at a really thin piece of gold foil, and almost all of them pass right through the gold foil. And you can tell because there's a little detector here. They could see little blips of light. This material is able to detect alpha particles. So they could see little blips of light so they could tell where the alpha particle landed. So almost all of the particles are passing through. Now, this isn't really showing you, let's actually click on these
Rutherford
actual results
observed that
here.
the majority of alpha particles penetrated the foil either undeflected or with only slight deflection. Every now and then, however, an alpha particle was scattered or deflected at a large angle. In some instances, an alpha particle actually bounced back in the direction from which it had come. This was a most surprising finding, for in Thomson's model, the positive charge of the atom was so diffuse or spread out that the positive alpha particles were expected to pass through the foil with very little deflection. Upon making this discovery, Rutherford explained, it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you.
So basically,
Rutherford's model to see the model of the atom that Rutherford proposed based on his experimental observation.
basically Rutherford was expecting, he was trying really to confirm the plum pudding model of the atom, and the plum pudding model of the atom really doesn't have anything in it that these alpha particles should hit. They all should pass right through, and that's what he thought would happen. But a very, very small percentage of them did not pass through because they hit something, and what they hit was the nucleus. Let's look at this last piece here.
Based on the results of his experiment, Rutherford postulated a nuclear atom. All the positive charge and most of the mass of the atom is concentrated in a very small volume called the nucleus. Electrons occupy the remaining space of the atom. The radius of an atom is approximately 20,000 times larger than the radius of the nucleus. Most of the positively charged alpha particles pass straight through the diffuse electron clouds of the atoms. Some alpha particles pass close to the small positive nuclei and are deflected at large angles. A few particles score a direct hit on the nuclei and come almost straight back.
So the nucleus is very, very, very small compared to the rest of the atom. An analogy you often hear is a ping pong ball relative to the size of like a football stadium. The nucleus is the size of a football stadium, of the ping pong. Kind of the rest of the atom where the electrons are flying around, that's the size of a stadium. And so all of the rest of that is empty space. And what's also kind of crazy is almost all of the mass, 99.999 whatever percent of it, is concentrated right there in that nucleus. So the nucleus is really small, really dense, and the rest of the atoms are empty space. So the fact that we sort of see things as solid, that is really more of an illusion than it is reality. Why don't you pass through your chair, since you and the chair are both mostly empty space? It has a lot to do with the fact that these electron clouds in your chair and in you have a very strong repulsion for each other. So that's what stops you from passing through solid objects. But, again, as you can see, here's what Rutherford knew. he knew the nucleus was really small because almost all of the alpha particles were passing through, like 99.999% of them went right through and didn't hit anything. So therefore the nucleus has to be really small. He also knew it was positive because alpha particles, in fact, are positively charged. And sometimes they would come close, like that one there, they would come close to the nucleus and just be repelled by it a little bit, change their course just a little. So since he knew alpha particles were positive, he also knew that the nucleus must therefore be positive. So if any of this stuff so far has blown your mind, what I'd suggest that you do is kind of go back, watch these animations again, listen to this again, and see if you can kind of wrap your brain around this gold foil experiment. Okay, so going back here, what we should definitely know is kind of a basic overview of the atom and what it looks like. We should know that there are protons that are in the nucleus that Rutherford discovered. There are neutrons which were discovered later by a guy named Chadwick. Neutrons are neutral and they have no charge. So the nucleus has protons and neutrons in it, and then the electrons exist in these things that we call orbitals, in a more refined view of the atom that we're going to talk about a little bit later. Relative mass. This is pretty important too. Really just don't overthink this too much. It just means these things compared to each other. Basically protons and neutrons are about the same mass, and we could give them a relative mass of 1, and they're pretty close to the same. Electrons do have mass, but they are just, even compared to protons and neutrons, they are really, 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 really tiny. So we can basically consider their mass to be about 0. Some terminology here. One thing that's important to know about protons is protons are the things that give an element its identity. What makes an element that element is how many protons are in its nucleus. So for example, you've all seen the periodic table. It starts out with hydrogen. Hydrogen has 1 proton, helium has 2 protons, lithium has 3 protons, and so forth. The fact that, in the case of lithium, the fact that it has 3 protons is what makes it lithium. If it had a different number of protons, it would be something else. So protons give an element its identity. Another thing we'll hear a lot in chemistry is ions. Ions are charged particles, so it's a general term for any particle that has a charge, either positive or negative. And how atoms are going to get a charge, it's not going to be their protons that are going to change, because the nucleus doesn't change in chemical reactions anyway. Neutrons are neutral, so it's the electrons that are changing to give it a charge. Now, when you say the word atom, or I, or anyone who's using the word atom correctly, if they're saying atom, that thing has to be neutral. If it's not neutral, it's not an atom. So, in an atom, protons, number of protons, the number of electrons will be the same, because their charge will balance out. If there's 5 protons, there's going to be 5 electrons in an atom to balance out that charge. Now, if it's an ion, those amount of electrons might be different. Another terminology, we have isotopes. And when we define things, as we'll talk about, you have to be very particular, and IB is usually very picky about how you define things. Isotopes are atoms with the same number of protons but a differing number of neutrons. The reason I underlined atoms in there is because sometimes people will define that incorrectly, like they'll say isotopes are elements with the same number of protons but a different number of neutrons. You would get that wrong on an IB question, because it's really the atom that has a different number of neutrons, not the element in general. But anyway, just a picky thing that IB does, I wanted to point out. So, for example, carbon. Most carbon atoms in Earth, anyway, have 6 protons and 6 neutrons, and we call that carbon-12 because 6 plus 6 is 12. So 6 protons, 6 neutrons, it's called carbon-12. There are some atoms of carbon that have 2 extra neutrons. They're called carbon-14, so it has 8 neutrons. So those would be examples of isotopes, carbon-12, carbon-14. Carbon-14 happens to be radioactive. What it means for something to be radioactive is the atom, the carbon-14 atom, is actually unstable. And over time, it will emit certain particles, particles of radioactivity, and in fact will turn into other elements, will turn into different elements over time. Now, some isotopes, this takes billions of years. Some isotopes, it happens relatively quickly, like carbon-14 is in the grand scale, is probably relatively quick in terms of how fast it decays. But we can use carbon-14 to do things like date radioactive, or rather date organic material. We can tell how old things are, things that were once alive. And the reason we can use carbon-14 to date things is, this is an important fact here, isotopes have identical chemical properties. So you and all other human beings and all other living things have a heck of a lot of carbon atoms inside of them. Almost all of those atoms are carbon-12, regular everyday old carbon-12, but a certain percentage of your carbon atoms are carbon-14 atoms. Now, to your body, these are no different. They behave exactly the same as all the other carbon. That's what I mean by isotopes have identical chemical properties. So in almost all circumstances, isotopes are going to behave identically in chemical reactions. Now, isotopes can have really slightly different physical properties like boiling point and density, but their chemical properties are the same. Some more terminology. The atomic number, now that's represented by a symbol Z, which is the number of protons in the nucleus of an atom. So every element has a different atomic number. It's on a periodic table, it's the whole number. It's the one that's not a decimal number, but that's always listed on every periodic table. And then we have the mass number. The mass number for a particular atom is the number of protons and neutrons combined in an atom. Sometimes those particles are called nucleons. Probably not a super important term, nucleons, but we should be aware of the mass number for sure. And then you have the relative atomic mass. If you look at a periodic table, you'll see every element will have a little decimal number on it. This is the weighted average of all of the isotopes of an element compared to 1/12 of a carbon-12 atom. So what this means is, first of all, there's a couple of parts here. There's the weighted average part, and then compared to 1/12 of a carbon-12 atom. Let me explain the second part first. You know, you have to weigh atoms somehow. You have to have some unit to weigh them with. So what was decided was you take a carbon-12 atom, and if you know how much that weighs, you divide it by 12, and that just becomes 1. So that's your basis for comparison. As far as the weighted average part, so again, with the carbon example, not all of the carbon atoms in the world have the same mass. Some of them are a little heavier, like carbon-14, and some of them are a little lighter, like carbon-12. So what you see on the periodic table is an average of all of those masses. That's the decimal number on the periodic table. That's the relative atomic mass. And that's why it's not a whole number. Now, you would think that you can't have half a proton or half a neutron, so you'd think the masses of all the atoms would be whole numbers, but what you got to understand is that accounts, the decimal number, the relative atomic mass, accounts for all the isotopes that have different masses. It's like when you see a statistic, you know, the average American family has 1.7 kids. Obviously, there are no families with 1.7 kids. It's not possible. That number is just an average. So it's the same with those decimal masses on the periodic table. You know, when you see, for instance, on a chlorine, chlorine's mass is 35.45. There are no chlorine atoms with that mass. There are none with that mass. That mass is just an average of all the isotopes, a weighted average. And we're going to talk more about what the weighted average part means too here in just a second. Now, you can take atoms, you can assemble them into molecules, and then that molecule will have a mass. And that's the relative molecular mass. Now, IB does a number of things a little bit differently. In the IB world, that relative atomic mass is considered unitless. However, most of the time, at least in my experience with chemistry classes in America, that number is called an atomic mass unit, an AMU. So that 1/12 of the carbon atom, that's called 1 AMU, and all the atomic masses are considered AMUs. That's the unit for atomic mass. But in IB, it's considered unitless. So, you know, I think we all have a friend like this white dog who likes to be the center of attention. But anyway, I thought I'd just show you that really quickly. So we need to get a handle on this notation. This is notation that we'll see. Here's the element symbol. Here's a charge if it exists. This top number is the mass number. Now remember what the mass number is. The mass number is protons and neutrons combined. The bottom number is the atomic number, so this is the number of protons. So this is an isotope of manganese. We would call this manganese 56. That would be another way down here to express this particular isotope. This, when you see it written out this way, this number is always the mass number. It doesn't, you know, when you say manganese 56, you don't need to be told the atomic number because you can look that up on a periodic table. It's the mass number that's going to vary for different isotopes. Again, I've mentioned this earlier, but it's possible that isotopes would have really slightly different physical properties like boiling point, melting point, and density. And I also mentioned earlier that some isotopes are radioactive, meaning they're going to emit small particles and decay to other elements over time. So to have different physical properties, you have to somehow, for instance, carbon-12 and carbon-14, you'd have to somehow find a way to completely separate them. If you had a pile of pure carbon-14 and a pile of pure carbon-12, you might find that you would find that their melting points and their densities are very slightly different. But again, chemical properties would be the same. How do you measure an atom, you might say? Well, you use a device called a mass spectrometer, and we don't have to know a ton of detail about this. In the old ISOTOPES, you had to know quite a bit more about it, but I guess what I'd like you to know for now is that the basic idea is that the atoms are separated and they are made to have a charge. And what they're done is, we can heat a sample of an element, let's say, and that element is going to be composed of different isotopes. We vaporize it, we give those things a charge, and we start pushing them through the mass spectrometer. And there's a magnet in the mass spectrometer which causes these atoms, these ions, to be bent. And they're going to be deflected by the magnet more or less depending on how heavy they are. So basically it's a way to separate atoms or small particles by size. And then we can detect where they are so we can tell how many of each size thing that we have. So it can tell you the relative mass, and it can tell you the percentage or the proportion of each one of those isotopes in a particular sample. So this is kind of a simplified version of the data you might get from a mass spectrometer. Now we're going to do some mass spectrometer problems here that I think are relatively easy, but we're going to do some later that are going to probably make you want to tear your hair out. Later, probably at the end of the second year. So anyway, suppose we want to know the relative atomic mass of this element here, and we put it into the mass spectrometer, and we know that there's 1, 2, 3, 4 different isotopes. Now, if we wanted to find the average, what we would not do, or what would not work, is to simply average these 4 numbers, add them up and divide by 4. There isn't any in 85. That wouldn't work. And the problem with that is it doesn't account for the fact that there's a lot more of the isotope with a mass of 84 than there is anything else. So that's why a straight average wouldn't work. What we have to do is we have to do a relative, rather a weighted average, which means multiply each mass by the proportion in the population. So it's not too hard. Let me show you. Now, relative abundance, it really doesn't matter. Basically, what it's saying is 82, 1 unit is 82. 1 unit is also 83. 6 units are 84, and so forth. So if we add these together, 1 plus 6, that's 8, plus 2, that's 10. So we know the total here is 10 units. And we're just trying to find a percentage here, so, or a proportion, or however you want to look at it. So it doesn't really matter what the unit is or how many in particular. We just know the total abundance is 10. So, therefore, the total is 10. 1/10 of the atom, 1 unit out of 10, is 82. So what we can do is multiply 1/10 times 82. We also know 1 out of 10 is 83, so we multiply 1/10 times 83. We know 6/10, reading from the graph, So 6/10 or 60%, however you want to look at it, have a mass of 84. So we multiply 6/10 times 84, and we get 50.4. And then 2/10 or 86. So this is what we mean by taking a weighted average. It's not a normal average. We're taking the numbers that we're averaging and we're multiplying them by the proportion in the population. So then we're going to simply add all those together, and we're going to get 84.1. Again, in IB circles, that's a unitless number. In other circles, that would be 84.1 AMUs. Notice a mistake that sometimes people make is they'll want to do these and then divide by 4 because they're used to doing that when they find an average. They'll divide it by 4 because there's 4 things. You don't need to do that. This has already taken care of that part of the averaging process by what we did here. So 84.1. Something to notice about this is it shouldn't be too surprising that the mass, the average mass, is pretty close to 84, since by far most of the isotopes have a mass of 84. So it shouldn't surprise us that the average is closest to that. Same type of problem, same concept in a slightly different format. It says chlorine exists in 2 naturally occurring isotopes. 75% of chlorine is chlorine-35 and 25% is chlorine-37. What is the A sub R, the relative atomic mass of chlorine? So we need to find the average mass. What we can't do is just take 35 plus 37 and divide by 2 and get 36, because that does not account for the fact that the amounts of chlorine-35 and chlorine-37 are vastly different. What we will do, similar to the last one, just working with percentages this time instead of fractions, I want to take 75%, but as a decimal, so that the math will work for me. I'm going to divide by 100, move the decimal over 2 spots. So change 75% to its decimal form and multiply that by 35, since 75% of the atoms are chlorine-35. And then I'm going to take 25% as a decimal times 37. So it's mathematically, it's the same concept as the one we just looked at. It's just working with decimals instead of fractions. But we get those 2 values there, we add them together, and we get 35.50. Now, if you look at a periodic table, that's going to come out, when you do this sorts of thing, it should come out very close to what's on the periodic table. It might vary from it a little bit because of rounding and things like that, but it should be pretty close. And when I check my periodic table that I have here anyway, it says chlorine's mass is 35.45. So we were pretty close at least. Alright guys, that's it. Thank you very much for watching. If there's parts that kind of blew your mind a little bit, or you're having trouble understanding, go back, look at those again. If you still don't understand, of course, talk to me about it. Ask me next class, and we'll get it figured out. Thank you, and have a